leuchtet ein Lämpchen und dann kann man reinsprechen.
Hallo zusammen. Hello everybody. We're gonna start in half an hour because there's some food outside. So if you like, grab some food, get a beer, and we're starting with Brandon in half an hour. Okay. So, hi everybody. My name is Timo. I'm from Giant Swarm, and yeah, I'm very glad that you all came to this meetup, and I'm also very glad that LinuxCon is in the town that shouldn't be named here. And so Brandon just wrote that he will be in Germany, and we can do this meetup. And that's awesome. And also the guys from ClusterHQ, Flocker, said they will come here. And so first talk will be by Brandon about Fleet and CoreOS. And the second talk will be by Luke about Flocker. And then we also have guests from LinuxCon from the Open Innovation Network. And they want to just shortly introduce what they are doing and why it's great. So thank you that you're here. So yeah, have fun. And yeah, Brandon.
Yeah.
So do you have another?
Yeah. I have some water. This is where all my personal email gets beamed up. Yeah, sure. No signal. Yay! All right, 1 second. Oh wow. You weren't kidding. Yeah, I know. I'm getting really nervous right now.
Keybase is nice.
Hey, there's my Linux Foundation email. Oh my goodness. For everyone's edification, the tabs are launching on the other display. Okay. We can't see Okay. So, how's everyone doing? Good. Good. Good to see you all.
Brandon has stickers here. We also have stickers.
Okay. Looking better. Hooray! Bigger. Yes. Okay, now we see a terminal. Let's see what I'm doing. There's one more terminal. So I can see what I'm doing. Cool. Immensely. Now, yeah, exactly. Now we have to play the game of what font size is everyone comfortable with. Can everyone see that? Yep. Okay. Okay. Great. Well, now that you've seen my desktop environment, I use OS X. So what I'm going to do in this talk is talk about Fleet. Fleet is a abstraction that we've created that's available under CoreOS for running a distributed systemd. Who here is familiar with systemd? Okay, great. I have good news for the rest of you. Systemd will be in your environments, whether you'd like it or not, in the next several years. So everything that I'll be teaching you today will be relevant in your careers soon. So I'll be covering how the system works and go over a bunch of examples of how Fleet and how Fleet might be used. So who I am, I'm the TO and systems engineer. I'm the CTO and co-founder of CoreOS. I've been a systems engineer for a long time. I started my career working at SUSE Linux, as a kernel engineer. So I spent early parts of my career out of hotels in Nuremberg. Right, and that's what I look like. I look like this right now, though. So in this presentation, I launched a terminal, so mistakes will be made. If you see me making a typo or a syntax error, please tell me, because I'm going to be busy trying to entertain you and probably not thinking about the syntax of the bash shell. So when I say clusters, I say Fleet is systemd for clusters. The first question that clusters are trying to answer is what are all these machines doing? Or from the point of view of the machines, what are all we doing? And so there's a few important things that have to happen in a cluster and a few important things that Fleet does for the cluster. So it registers machines into the cluster so you know who your peers are, who the other members are. It is getting work out to the machines in the cluster. So I have some schedule of work that I like to have happen, and Fleet ensures that that work ends up on a machine. It does a number of things like schedule based on criteria. So some people may, or some machines may be more fit for work than others because they have special hardware, they have special location. So you may be wanting to design something for fault tolerance and failure domains of, West Coast, East Coast. And then the last thing that Fleet does, and that's important for the cluster, is that it keeps the process running. So if an individual machine dies in the cluster, Fleet's job is to ensure that a new machine is selected to run that work. So it's answering the question of what is everyone doing? I've already asked the question of who's familiar with systemd. It looks about like half the room. So I'm going to go over a quick overview of systemd and why it's important. So this is an example service file. A service file defines a unit of work. If you're familiar with sysv init, this is about 400 lines of bash compressed down into 2 lines of a configuration file. If you've used upstart, it's very similar to upstart in that it's more or less a compact declarative format. But you say, I have a service, so there's a service section to the file, and then I say where the service is. And in general, services under systemd don't do any double forking. They don't do any daemonization. Everything is put inside of a C group, and systemd takes care of forking it out as a daemon. So along with just starting the process, it does a number of other things. It sets up the environment for the application to run in. You can optionally do things like put limits on C groups. So say this service is only allowed, 512 megs of RAM, or it's only allowed half of a CPU, where half of the CPU is this very fuzzy definition left up to shares within the kernel. But you have some type of relative weighting ability, or in terms of very explicit things like disk or network IO, very explicit weighting. And then also systemd has a number of sections to help us humans understand what the system's doing. So we can add arbitrary descriptions or URLs, which are great in moments of panic of where bugs should be filed or where to find the documentation. So you can add those sorts of sections to your systemd units. And so one of the questions that we've gotten asked once in a while is, why not just write your own executor? It's so simple. You just fork out a process, and then you just hook up standard IO and standard out. It's simple. Well, honestly, systemd buys us a lot of, it does a lot of work for us. It's API driven, which is great because it means that we don't have to import some sort of library into our tools. We just talk to it over a socket. But it also does a number of things. Setting up a Unix process is fairly complex. There's environment variables. There's setting the current working directory, the users and groups that actually run the process. Now C groups. We have namespaces now. We have CPU and affinity, which is important if you're running some sort of VPN or something that's dealing with the flow of information and you want to keep a hot cache. You have dependencies. I need this thing to start before that thing. You have set comp filters. Can't forget about those. You have resource limits. And you may have capabilities too. The list really goes on. The Unix environment is much more complex than it used to be. There's no longer just, oh, I just fork the process and everything's going to be fine. And over SysB in it actually buys us a number of advantages, having a very explicit declarative way of saying, this is the process that I'd like to have started. In SysB in it, we have this problem of environment variable leakage, where the user will do sudo su, and they'll have some important metadata in their environment, and then they'll be like etc init d apache 2 start, and anything in their environment ends up in the child process of that thing that they just forked off. Right. So systemd helps fork it out, but then it also is an active process. There's things that we want our init systems doing. We want our init systems, restarting things when they fail. Restarting a process because the OOM killer killed it, or it hit a seg fault or something, is a pretty, normal mechanism. It's something that you want. Who wants to get paged at 4 a.m. because some random thing went out of memory, or it had a leaky file descriptor and it got shot by the kernel? Everyone wants to be paged. Who wants to get paid? So people want to have their systems take care of themselves a little bit, and this requires a set of active monitoring. And so it's not just monitoring of when things need to be restarted. It's when this service has no more processes, that's when it stopped, not when the PID file no longer matches an active PID. There's a number of active processes that should happen and that we should expect out of our computer systems. And so I mentioned earlier that systemd is API driven, and we utilize that API. We have a Go library for systemd that we use all throughout Fleet. So we just talk to it. We say start unit and give it a map of the things that service needs to start, and then systemd just kind of takes care of it. Who here's used Go, the Go programming language? Okay, wow. You all need to be using Go at some point, at least playing around with it. It's really amazing. There's a project at LinuxCon that somebody was talking about, where he's started to go through and just re-implement all the Unix shell commands. So like cp, move, ip, sudo, these sort of things. And it's amazing. You look at the GNU source for these things, and then you look at the Go source, and it's just so compact because we've abstracted out things like opening up file descriptors for streaming and error handling around those things to the point where the code can be very compact in Go. Right. So yeah, systemd has an API. It's really good. It does some interesting things. Okay. So what I wanted to do here was talk about cluster schedulers. Also to poll the room, I know your hands are probably getting tired with all the raising. Who's used a scheduler-based system where you just declare what you want and then it gets scheduled out to machines in your cluster? 2 guys, one of the giant swarm guys. Okay, not many of you. So a scheduler system is something that is a fairly common pattern in large organizations. The reason Google engineers are so efficient and effective at launching products is because they are not infrastructure engineers. They are they think about building software, and then they have infrastructure upon which they build more software that gets that software running. It's not something where they're thinking about switches and computers. It's if you talk to a Google engineer, it's pretty ridiculous how little they care about, you know, an additional couple terabytes of network traffic, you know, because of product launch. Okay, cool. Tell me when it launches because I want to try it out in beta or whatever. Schedulers are a really important concept because, again, what we're doing is we're pushing the abstraction down on the computer and saying, hey, I mean, your lives as computers are interesting, you're Turing complete and everything, that's awesome. But like, I want you to figure out the difficult parts for me. I want you to figure out, hey, I want 8 units of this thing running. Just choose some of you amongst you to run the work. Okay. So this joke's wearing thin, but I spent a lot of time on these graphics, so I just really want you all to appreciate these. These are expensive graphics. So you are the user. You are the user here, as noted by the eyes and smiley face. This is a schedule of tasks that you'd like to be running, and you push the schedule of tasks into the schedule API. It's fairly straightforward, and this is the basic workflow of how these schedulers work. You say, do this thing, and then the API figures it out. And the scheduler's job is to take that schedule from the user and then split it up. So he has an idea of, you know, what resources are available where the failure domains are, you know, where the network switches are, where hardware is connected to the same power line, etc. Really advanced stuff can happen in the scheduler. Or it could just be divide by 3, and then those jobs get evenly distributed over the machine. But the important part is that this is an active process. So the scheduler needs to have information on who the members are, who's currently available to do work. So at some point, machine C, if you missed the animation there, it's pretty substantial. If you lose machine C, the scheduler now has some work to do. The scheduler needs to be like, oh, well, machine C was running task 1, so I need to reschedule task 1, and I need to get that landed on machine B in this case. And if everything goes successfully, then that process resumes handling user data. The engineer who's trying to get some sleep continues sleeping, and everyone is more or less happy. Except for the hardware that died. We can't save him. And then how this looks on the machine is that the machine has generally what's called an agent. Depending on the scheduler, it can be a kubelet or whatever. We call it a fleet agent. And so it takes its individual schedule, and then it, in fleet, talks to system D to make that schedule true. So it says, I have these processes, and I need to ensure they run. All right, so we've defined what a scheduler is and why it's important and what it does for us humans, which is the most important. But we have a bit of a problem now in that we've just defined that the system is tolerant to machines failing. If you all remember, and more in the loss of machine C in the previous slide, we want the system to be resilient. And so we have global state, and that state is the configuration and the members and the individual schedules of each machine. This is global state that needs to be viewable even in the face of machine's failure. So we need to have a holder of this global state, and that's where etcd comes in. Who's used etcd or is familiar with the concepts of etcd? Okay, great. This will be a fast overview, so you won't get bored. So etcd is a really cute combination of 2 things. It's /etc distributed. So we took the D and the etc. It's essentially the same semantics that you want from etc /etc. It's distributed over a number of machines, and there's a number of semantics that we enjoy out of a POSIX file system that are extremely difficult to replicate over the network. And the main attribute that we enjoy is the ability to do atomic operations. And the atomic operation, the only atomic operation that we're afforded in POSIX, is the ability to do an atomic rename. And at D, we're able to do an atomic compare and swap. And that's the primary semantic and the primary important thing for etcd is that it's a distributed way of doing atomic compare and swap operations. So I have value A in, I have key, let's say I have file A and it has a value of 1, and I need to ensure that atomically I can switch that value to 2. Okay. So some of the important things about etcd is it's open source software. You can get it off GitHub. It's Apache license. It's highly available in the sense that it's tolerant to machine failures. It's sequentially consistent, so when things happen, they happen in the same order for all members of the cluster. You can ask for getting updates on changes through etcd. So if I'm interested in file A, it's similar to iNotify. I get notified when that thing changes. The important bit is it's exposed via HTTP because we're going over a network and people know how to interact with HTTP through Python and whatever their native languages are. It's really scary and interesting that people have started like writing master election scripts using curl and bash. So they like master elect their database using some curl to talk to etcd, which is frightening and pretty cool at the same time. It's runtime configurable, so this is important for the environments that we end up running a lot of our infrastructure in these days, where a machine goes away and it was one of the etcd members, and we want to ensure that we can remove that member who's never coming back and add a new member. And similar systems like Zookeeper haven't really had this mechanism. Okay, so the API is straightforward. You get to get things, you put things, you delete things. Any questions? And the basic idea there is that you get keys. So I say value A, and then you get the body of A, and you put things, and you can create keys that way. All right, so etcd is a distributed system, and so whenever we're talking about a distributed system, the important thing is to talk about its partition tolerance, or in non-computer science terms, its resiliency to machine failure. So in this case, etcd is available. This is a 5-node cluster. Everything is fine. We lose a node and everything's still fine. It's resilient to a single machine failure in a 5-node cluster. And it's resilient to a 2 machine failure because we still maintain a simple majority of the cluster, 51, a simple majority. And then once we lose that last node, etcd is now unavailable. And at this point, depending on how your client is interacting with etcd, reads may, or writes will fail. And reads may or may not be serviced, depending on your consistency guarantees of your client. Demo time. Now we get to try to type while holding a microphone. Do you have any solution to this? Okay, thank you. Okay, sorry. Okay, so we logged into one of the CoreOS machines. I have a 3-node cluster running on this machine, and hopefully it survived the multiple suspend resume cycles that it's gone through, because Vagrant's not the best. So I'm setting a key here, foobar, to the value 123. Don't tell anybody, but this is my default password for many things. Let's see. I need to adjust this window size. It's gonna be fun.
No photos.
Yeah, this is my password.
It's fine.
There we go. Okay, there we go. Okay, so it immediately returned, 123, because that's the value of the key that I just set. So that's sort of interesting. The the one thing that we can see here is we have this handy debug flag, which prints out an example of how to run this through curl. So you can see that it's an HTTP based API, which I promised you it was. So we'll just do this really quick. And so you get some JSON back, which describes the state of the key. So that's kind of interesting. One of the features that is also useful and then we use quite a bit is that we can watch keys. And so I'll set on this other machine, node 1, I'll set a watch and it just hangs because it's waiting for an update to that key. And then on this other machine, machine 3, I'll do a set, and we'll do a password rotation here, and I'll set it to 321, and I get 321 over here, and then obviously that happened a lot faster than I can. But anyways, so it immediately returns and gets the value of that key. Sorry, it's a long poll. Yeah, so it connects and it says I'm willing to wait for the next value, and then the etcd leaves the connection open. Yeah, people have asked for other methods like having what are they called, WebSockets and that sort of stuff. Perfectly reasonable. I'm personally just waiting for HTTP 2. Right. Cool. So etcd. That's how it operates. We use it in a number of different ways, and we use it for these compare and swap operations. So in conclusion, etcd's job is to not lose stuff in the face of machine failures. It's also in charge of ensuring that we can make atomic changes across the cluster. All right, so Fleet, we've finally gotten through all the preamble, and we're 22 minutes in. So Fleet is the actual scheduler and agent pieces. So the scheduler piece is, there's only one scheduler, just like, there's only one boss. You have to have somebody who makes a decision and then everyone else follows. Otherwise chaos happens. And so the scheduler and the agents are the two pieces. And the agent lives on every machine. The scheduler is leader elected. So he's elected by everyone else to make decisions. And so in this case, we have a systemd service file, and the service file, looks like a service file looks. And in order to start it on a single machine, under systemd, we would say systemctl start the service file. And then the user interface change that we introduce in Fleet is that you change that to fleetctl start, and then it gets scheduled and runs on another machine. So that's the transition between systemd and Fleet. And sorry, I'm gonna have to ask for the microphone stand.
I hope you don't do a long live coding session, right?
Okay, so let's see. I'll skip out on a lot of typing here. I'll use one of these other files that I already have sitting here. Let me destroy anything that might have existed before. Oh. Okay. So we have. Okay. So what I'll do here is I have a single service file. It's bar at service. So I'll do fleetctl start bar at 3.service. And then what happens here is this gets submitted to the scheduler. The scheduler will notice the works come in. One of the agents will pick up the work. And then once the agent successfully started that work on the machine, we get notified back as the user. And when I set this demo up, I didn't have really good internet access. So instead of a Docker container or something interesting, it's doing the classic daemon of sleep 4000. But you can imagine this being some long-lived process that's interesting. Thank you. Right. So that's the basic mechanism of how Fleet works. Right. Okay. The other piece of this is the Fleet engine, and the engine is the thing that exists on each machine. And like we had seen earlier, its basic workflow is to take the schedule and run it. So, wow, I really screwed that up. The engine is the thing that exists once in the cluster. It's the singleton, it's the scheduler. And so its job is to take the global state and schedule it out. So we saw this diagram earlier, and it takes the schedule that came from the human being, runs it through its algorithm, and then splits it up into work that runs on the individual machines. Based on machine health, it then updates the schedule and continues doing this. There's a number of things that the scheduler can be hinted to do. So the scheduler can be told, hey, ensure that this work is running on this particular machine. So you can essentially tag it and say, ensure that it's running on this machine that's in the West Coast or something. You can say, ensure that this is running somewhere that's next to a Redis service. So you can say, require that this work is on a machine that has process running. Or you could say, ensure that it's running on this very particular UUID of the machine. So there's a number of constraints, essentially, that you can put on the scheduler's decision making. So in the case of Fleet, we've added a systemd section called X. So it's like HTTP or something, where in systemd, it'll ignore anything that's prefixed with an X minus. It's a convention to say that this is a user-defined or a vendor-defined extension. So our extension is X-Fleet, and then the section is conflicts. So in this case, my service, for whatever reason, does not want to land on the same machine as not my service. And so when you start this, the scheduler ensures that this constraint remains true. All right, so the Fleet agent is the other component, and it's the part that takes the schedule of an individual machine and ensures that state actually happens as a running process. Again, from the diagram, machine sees schedule that comes down from the scheduler, goes to the agent, and talks to systemd. Demo. Okay. So I kind of forget which thing I just started. It doesn't matter. Okay, so right now in the cluster we have the service bar3 that's running on this random number host here, 1C66. It's active and running, so it's reporting that the state of the process is healthy. And the bar service has a conflict section. So in the service file, it says, sleep 4000, but that it conflicts with any other bar service. So what this defines, this simple conflict section, is it defines that this bar service is only running once on any given host. So when I do, I'll start 2 more of these things. I'll call them 1 and 2 for lack of a better name. And what should happen is the scheduler gets these units with the constraints, and then it schedules it out to the other 2 machines. And yeah, lo and behold, the software worked. And you'll notice that all the IP addresses are different because it ended up on different machines. Cool. So we're going to play the guessing game. Shoot. Uh-oh, I can't type. So what happens when I start that 4th unit in my 4-node cluster? Like, why is this hanging? Why is it not telling me that the machine the job is being scheduled correctly? Exactly. So this job is just sitting there in the queue of runnable work. There's nobody available. So it'll just sit there in the schedule forever. And this command line tool is told to hang until the work gets queued or goes through the queue and actually gets scheduled. So in this case, nobody can take the job. It sits in the scheduler until additional machines show up. 3 node. Yeah. So yeah, those are the machines in the cluster. 1C9A F2. Great, thank you. Okay, so for all those ops people watching at home, you're probably thinking, oh, great, awesome. So you've now just splatted all of this stuff all over my infrastructure. Thank you. That's really helpful. The next natural piece in all of this is service discovery. So great, the work is running somewhere in the cluster. Now where is it? So I can add it to a load balancer. I can actually get useful customer requests going through the thing. And so there's a few different ways that this happens. The way that we use it internally, and that a number of people have been using it, is you do the registration yourself. So etcd is a key value store, and its primary use case is for leader election and service discovery. So having your container, your application do this registration itself is a very natural thing. And this is how it works in a lot of large scale operations, is that they provide some type of client library to their service discovery daemon that every time a process comes up, it does its registration of the keys and values that are important to the application, whether it be its IP address and port, or its secret keys, whatever it is, it does some sort of registration of itself. And there's so you can do homegrown things. There's if you are using HTTP or TCP, there's a really nice load balancer that one of my former colleagues from Rackspace built on etcd called Vulkan. And so you can have your HTTP endpoints automatically register themselves into vhost, and then they get work out of that vhost, and it does really active health management of that vhost, ensuring that the backends are actually successfully returning 200s to the user, etc. So one option is to do service registration yourself. The other option, which is a little more complicated, and I think you've actually talked about here quite a lot, is the idea of getting some help from somebody. And this help in Docker, in a lot of cases, comes from the ambassador pattern. And so who's familiar with the ambassador pattern? Okay, the idea with the ambassador pattern is that I have no idea what's going on, so I'm going to rely on somebody else to do the orientation of the environment for me. So in this case, we prototyped out an ambassador that was a simple TCP proxy, and so you start a Docker container for Redis, for example, and then you also start a simple ambassador, in this case, simple amb, that registers this Redis machine into, or this Redis process into etcd. And then it gets a little bit more complicated. So the Redis, or the ambassador, registers into etcd, and then there's another ambassador on the other side for the Redis client. And so that ambassador for the Redis client talks to etcd. It's like, where is the IP and port of this the server that I'm supposed to be talking to? And so the TCP proxy takes Redis commands, and then it proxies them to the correct IP and port for the actual running Redis container. That's how that works. All right, so the next piece is fleetctl and the API. We have a number of really interesting and cute tricks that I hope convince you all to learn Go that we use in fleetctl. Really, the amazing part of Go, I think, as somebody who's implemented language bindings to OpenSSL twice now, is that they've implemented all the key crypto standards directly into the language, or via really well-maintained libraries. So I wrote an X509 certificate authority along with one of our interns in Go, and it was a few hundred lines of Go, and it's a fairly robust tool that I think arguably makes a much easier experience than the OpenSSL X509 tool. Who here loves the OpenSSL X509 tool? That .conf file, it's really awesome. I love having just lots of different ways of specifying a list of values. I think that's my favorite part of that file. And so Go builds in all of these really useful useful crypto primitives. And the one that I'll show off is that they have built in an SSH library. So I can actually do SSH from pure Go. You can also do GPG from pure Go without having to talk to the GNU PG tools, which is a godsend for anybody who's trying to like sign and verify files, because GPG is kind of the standard format for doing file verification with a public key, for better or for worse. All right, so I'm gonna need microphone stand. Thank you.
There are people making jokes on Twitter.
Oh yeah? Dang. Sorry. Okay, so I guess the first thing I'll show is that we have an API. Uh-oh.
We had an API.
It's not running. Okay. I must have failed to start the correct socket. Anyways, so there's an API that the problem is curl doesn't allow you to curl Unix sockets. It only allows you to curl TCP sockets. Arguably reasonable. But there's a socket that you can talk HTTP to do all the same things that fleetctl allows you to do from the command line. You can drive Fleet via an API. And all the APIs that we've built so far at CoreOS use the concept of a discovery JSON file, which I think more people should use, because I feel everyone's like, oh, we expose it via REST. Like that solves all the problems. Like I've exposed this thing via REST. But the moment people get past the like demo stage of using your API, the next thing they ask for almost immediately is, I want bindings in Python and Ruby and Java, and then probably Go, and then Node.js would be nice. And they kind of, you end up with this laundry list of languages that you maintain this API for. The idea of a discovery JSON, and all the Google APIs have this discovery JSON file. Sorry. Have this discovery JSON file. The basic idea is that I just define all the structures that are important to my API, the JSON structures and the API endpoints, and then I can automatically generate client bindings. So Go client bindings, or Python client bindings, or Java client bindings. And we use this internally quite a bit at CoreOS on our APIs, because it just saves us time. I don't have to, check for a non-200 error code and then return an exception in whatever format that language expects, and write this sort of wrapper code over and over again. So the other thing that is sort of nice, so we have an API, but also fleetctl. Fleetctl allows you to do interesting things. So right now I'm on, well, it sometimes allows you to do interesting things. Okay, so what I'm doing here is I'm saying fleetctl journal bar at one.service. And I gave it this environment variable of the SSH endpoint for one of my virtual machines. So the fleetctl tunnel, this is the machine it'll tunnel through to make requests. So of course, this is the first time I'm connecting to this host. So it's asking me to confirm, never do this in production, but it's asking me to confirm the fingerprint. And so I blindly type yes. And what happens is it actually pours out the logs. So it SSHs into the correct machine that's running this host, and it streams me, from my Darwin host here. This is running not Linux, so it's not systemd and it's not Fleet. It's streaming back the systemd journal output to my host. And so I can do essentially anything that I was doing from the Linux command line remotely. And it's all kind of transparent to the user. And it's a really nice way of administrating clusters of machines, is kind of having this transport agnostic thing that you don't have to worry about setting up TLS and running a certificate authority to protect these HTTP endpoints. We just say, we're going to tunnel in through a bastion that you define, and use SSH to kind of bounce ourselves around the environment. There's this really cool project that I had an intern work on this summer that's a SSH certificate authority. And I hope to write a blog post about it in the next few weeks, because just blindly saying yes when you first log into a machine is better than nothing, but I think we can probably do better as an industry for the security of the most sensitive port on our infrastructure, port 22, than to just blindly assume that connecting the first time is secure enough over the long haul of the machine's lifetime. Okay, so that demo is over. Thank you again. So future work. There's a lot to do in Fleet. It works pretty well now. We use it to service a lot of our internal infrastructure and customer-facing infrastructure. But we'd like to see better Docker integration, and it's something that we've been working on in various ways. We'd like to release the API officially. The API is currently v1-alpha, which we hope hints people that this may change and go away soon. So we want to remove that -alpha. Security is something that I'm super interested in, and I sort of the team forced through a feature early in the lifecycle to do SSH key signing. So when I update the schedule, I actually have to sign that request, the new schedule, with my personal SSH key from my workstation. The idea being that the host then needs to confirm that that schedule entry that ends up getting scheduled to their host is signed by a key that they recognize. So that is that administrator would be allowed to log into the machine and actually run that command manually via the public key of the SSH. And so that's a feature that we had, and then we removed it because it was slowing down our ability to quickly iterate on Fleet. So we'll be re-adding that. But I think there's some interesting things that we can do around permissions to run things on individual machines. Multi-tenanting of projects. So currently, Fleet is very much like systemd. It's very flat. So there's only one PID1 to rule them all. And Fleet has a very similar point of view right now. And then helping out more with service discovery is something that I think we can at least aid, if not help fix a little bit. I'm not sure exactly how that looks, but something that I think we can continue to push on a bit. So, right. That was Fleet, one of the CoreOS projects. All of our projects are open source. So Apache, all the projects that I've covered are open source. So Fleet and etcd are open source. CoreOS itself is open source. You can go to our website and build CoreOS from scratch using our SDK root. We love pull requests. We love bug reports, not as much as pull requests, but we still love bug reports. Yeah, we build stuff. Yeah, we have some interesting products, including a Docker registry and a product for managing the rollout of CoreOS updates, which I'd encourage you all to check out. And we're also hiring in San Francisco and New York. And we haven't hired a European quite yet. It's something I'd like to do, but it just hasn't found the right situation yet. So that's Fleet. That's my pitch on CoreOS. And if you have any questions, I'd love to answer them.
So you said that Fleet restarts services when they crash automatically. Would it restart them on the same node or just on any other? And what if the process needs some file system access?
Sure. So Fleet only restarts or reschedules work if the machine has died. So yeah, so we rely on the systemd process to monitor the processes on the host. So after we give the work to systemd, the Fleet's job is done. So in systemd, you can define restart policies. You can say if it's died because of this exit code, or if it died because of this signal, then restart it, or restart it with these retry intervals, and then at the end of it, stop. And so we rely on these mechanisms. So a user who just always wants it running on the host, no matter like how terrible the environment is, they can set restart equals always, and then that's what Fleet and systemd will do for you. So we only help in the machine failure case.
I remember a while ago, Etsy had problems with reliable CoreOS, which apparently wasn't tested enough to deal with network partition. In the aftermath of that, have you developed like a really rigorous testing schedule? Like how do you test all the distributed systems that you have with input that ran in a platform?
Sure. So I gave a talk recently at a meetup. You can find the video. It's talks about what's currently in the master branch of etcd. But the short of it is that we recently implemented a new like fairly major refactor of Raft, and we took into consideration some of the failure cases that we'd found in our old Raft implementation. And so the hope is we've gained a lot of confidence in that Raft implementation, and the next release will be using that as its Raft. And the nice thing about some of the changes we made is that we have removed time from the tests, which means that the times are faster, but it also means that the tests are fully deterministic. Because at the end of the day, these distributed systems don't care about time; they care about the ordering of events. And so we've kind of headed that off by fixing the problem at its core, and so that's what we're doing.
Ah, that's better. That's now a question about TCD. I've actually tried to use it.
Yeah.
And what I miss are two things. First of all, not only compare and swap for single values, but also larger transactions. And secondly, some kind of callback service. So I wished not only to be able to watch a single value or single directory, but I wish to be able to see if something has happened, maybe via an HTTP call in the other direction. Are there any plans in that direction for these two questions, or are you saying you're happy with compare and swap and that's it, and watch?
Yeah, so etcd is a component in Kubernetes, and they've brought up similar concerns and questions. I think where we'll start with the multi-request thing is there's a pretty urgent need in Kubernetes for multiple gets in a single transaction. So we'll probably start there as the first API extension, and then we'll start to feel out the multiple key sets. They are a little bit more complicated for us to do internally, but I understand the use case quite a bit. So no promises there. I will promise that we will add multi-git. Multi-set is a little bit more complicated. As for the callbacks, so one of the things that we've learned quite a bit from talking to people who've been using similar systems in production is that the one and like constant systems is that your clients will be extremely abusive, because these are the pieces of infrastructure that people test the least, because it's like, oh, I got my code working, awesome, 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 and then service registration, right? I need to do that. So they write tight loops. They don't think through the retry logic, etc. And so on the callback thing, what I really like to see is we've done work in the next version of etcd to allow for observers. I'd like to have somebody prototype out callback models that don't involve the quorum, because the quorum already has a ton of work to do in a busy cluster. So I'd like for this concept of a read-only observer to be able to service these sorts of requests by saying I just push a copy of the log to this observer, and then they are able to service callback requests, or they're able to service these watches, these read-only operations without the help of the quorum. And I think that will help alleviate a lot of the use cases, because people end up using these systems a lot because they want to update load balancers, they want to update DNS, and load balancers and DNS don't need to have, in a lot of cases, they don't need to have a fully consistent view of the system. They need it consistent, or they need to have a time bound on when it's inconsistent, so that they can like fall back and talk to the quorum. But there's a lot of use cases we can solve with this observer stuff. So I'm optimistic on there, but I have no solid plans, and I'd love to see like an API prototype of like what people are thinking through as far as webhooks and callbacks. So I punted on a lot of things there. Sorry, but that's the state of it.
Have you some plans to add on etcd some authorization stuff that not only every request can read all?
Yeah. So that's something that I've been thinking through quite a bit, and I know the team has too. Kind of waited for a while to feel out what the requirements there were. And I think it's pretty clear that people have two use cases, and we need to make them both happen. The first use case is they want to have all of the ACLs go through the log. So they want to have an audit trail of who requested an ACL and what that request was for. And then people also want to have the ability to have crypto keys so that they can filter out requests on the edge, again, to protect against these abusive clients. So we've been playing around with various API specs, and it's something that we'll probably add in 0.6. So it's going to be a few months, but it's something we're thinking through, and we want to like get it right the first time. So. Oh, and right now we currently have TLS and client certificates, but that doesn't protect the key space. It only protects clients connecting. Okay. Thank you so much for your attention. Appreciate it. Thank you.
So next talk is by Luke from ClusterHQ and Flocker. So any demo planned?
Sorry. Actually, I have some recorded demos that I'm going to stand up and point to.
Perfect. Yeah, perfect. Huh? Yeah.
Great. Awesome. Thank you. Do you have the adapter? Brilliant. Sorry, you're clearly a professional because you carry one of these with you. Someone turn the projector on, please. Cool. Well, great to see so many people here tonight. Thank you. As a sort of, I'm quite pleased with the ordering of these talks actually, because this is a follow-up to a talk about clustering Docker containers, in which I'm going to talk about one of the sort of advanced topics for clustering Docker containers, which is how you deal with state or data in a cluster of containers. So if the projector works, then I can get started with that. Oh, I see lights. Huzzah! Works. Okay, wonderful. I guess it'll warm up slowly. Anyway, cool. So first up, I think we can probably all agree that Docker is pretty awesome. Clearly won the hearts and minds of developers and DevOps people as a sane way of packaging up applications and their dependencies. And it's, for me, the big win really is that it's got people to start using containers in a big way. And I think that Linux containers are a fundamentally better way of abstracting applications than virtual machines. Containers are lightweight, they're portable, they have better performance, and you can fit many more of them on a box. They have much higher density than virtual machines. So it's fantastic to see a movement that is pushing people to use them more and more. However, there are some things that are difficult to do with Docker and container management systems today. And the reason for that is that as soon as you want to put an application that's containerized into production, you need some sort of orchestration system such as Fleet or Kubernetes or Mesos or Cloud Foundry, but none of these systems support stateful services. And so what you see is that you can only actually deploy half of your application. So let me explain what I mean by that. If you look at sort of typical modern sort of microservices-based architecture, that's what's trendy now, right? You might get some scale-out API servers and some scale-out web front ends. This is actually a massive simplification because there's no logging or caching in this diagram. Sorry? No one? Okay. And you also, these API servers talk to probably some NoSQL database and maybe a Postgres or a RabbitMQ. And so do the web front ends because things are complicated and messy. And containers and platform as a service currently only capture this right-hand side. They only capture the part of the application stack which doesn't store data in the file system. What my view is that we should actually aim to capture the entire application and be able to consistently deploy the entire application across dev, staging, and production environments using the same sort of way of packaging these applications for both the stateful and the stateless components. And that's what I'm going to talk about tonight, because there's a sort of certain set of problems that you get when you try and manage data in containers. And so this is the big problem we're solving at ClusterHQ. We're working on solving for stateful container clustering. And in particular, we're interested in solving the data piece. So we're also really interested in, and I'm personally interested tonight in figuring out from you guys, what should we integrate this with? Because we've got this sort of stack of technology that does this, and do you want to see it with CoreOS, or do you want to see it with something else? So I'm really interested in hearing that. And just to motivate this a little bit, as soon as you deploy data into production, putting the stateful services into containers is actually the easy bit. You can deploy like MySQL or Postgres in Docker today. That's easy. The difficult bit is then doing the sort of operational management things that you want to do to that data once it's there, such as backing it up, moving it around, replicating it, and recovering when hardware or software or cloud infrastructure fails. And just to motivate this a little bit further, as soon as you run stateful services in Docker, Docker best practices dictate that you should attach a volume to the container. And assuming that you're using something that looks like local storage, including cloud VMs, that container then gets stuck on that specific physical or virtual machine. And this violates this principle that you should treat your servers in the cloud like cattle, not pets. Has everyone heard of that before? So the idea is like, as soon as you have a server and you name the server and you start caring about what's on it, then it's a pet. And if that server dies, then you'd be sad. Whereas you should really treat your, I've got Randy Bias to thank for this one, so thanks, Randy. But as soon as, if you can instead treat your servers like cattle and any one of them can die and the system can just carry on working, then you're in a much happier place and you don't get paged in the middle of the night. So that's how we should be managing our infrastructure and our storage. But it's tricky with Docker because as soon as you put a stateful thing in Docker, then it gets stuck on that specific machine, and that machine becomes a pet, and you don't want that. So as people who care about ops as well as dev, actually, quick show of hands, like who in the room describes themselves as an ops person? Okay, developers? Cool, okay, interesting. So developers, there are ops people as well, and we need to stay happy. So we care about the following things. We care about robustness of systems. We want to eliminate single points of failure. And to me, what that's all about is about abstracting applications and their data away from the underlying infrastructure, just like virtual machines did. And so VMware did a brilliant job of doing exactly that for ops people. They abstracted the concept of a computer into a virtual machine and ran it on a cluster of machines such that if any one of those machines failed, or if pieces of the typically SAN storage that it was connected to failed, then things would carry on running. The problem is that now that we're moving into a containerized world, we don't want to have to put one container in each VM. In fact, it would be better, in my opinion, if we could get rid of VMs entirely and sort of kick away the ladder. So what I'm saying is we should try and build systems that can manage from an operational perspective the sort of things that you expect to be able to do with virtual machines. We also care about scalability. It would be nice to be able to just like scale up a cluster by throwing some more servers at it. And we want to reduce complexity, so we want to have systems that we can actually manage. And I think that sort of a key to solving this ops problem is the ability to move things around. There are multiple reasons why you might want to move a container and its associated data around from one machine to another. You might need to upgrade the RAM in a machine. You might need to upgrade the BIOSes in an entire rack in your data center. And wouldn't it be nice if you could just drain all the containers off that rack and move it onto a different rack and then move them back again after you've done your maintenance? So anyway, it would be really nice to be able to move things around and also to be able to fail them over if they fail, and crucially to do that on a container granular level. So for an entire cluster of containers rather than a cluster of VMs. So there are some goals. It would be really nice to have a system which is, well, I hope I've already convinced you that we need a system which is multi-node. Pretty much as soon as you put an application into production, you need to run it on multiple machines, both for performance and scalability, and also for resilience purposes, because computers are fallible. And it would also be great to have a system which we can manage. And for me, manageability of these systems implies a certain number of characteristics. The first one is a homogeneous set of servers. And the reason I like homogeneous servers from a sort of functionally identical perspective is that if all of your servers are homogeneous from a functional perspective, then any one of them failing means that that machine by definition wasn't special, and therefore any other machine in the cluster can take over and carry on doing the work that it was doing. No single point of failure is really nice because that means you can never get woken up in the middle of the night. And to me, no single point of failure actually implies multi-region. So we need to support systems that can run across multiple data centers, because as much as you try, every data center is a single point of failure eventually, because, for example, it might get flooded. So anyway, just a final point on this, the data services that the cluster depends on actually have to be protected by or within the system itself. And so, for example, etcd inside Fleet is a good example of this, because it itself will cope with and be resilient. So there shouldn't be some external data services that need to be separately managed and configured. Otherwise, you've just punted the problem off to someone else. And so a crux of all of this stuff that I've talked about, that sort of the consequence of this, is that we need to have containers which are portable. We need to be able to move containers around even when they have data associated with them. And therefore, the system has to expose portable resilient volumes. So I'm going to talk a little bit about a proposal I've got for how we can go about doing that. And just quickly, one other point is that when you move things around, you'd like it if the services that depend on those services that you're moving didn't notice that the moving around happened. It's sad if you end up having to restart a bunch of services because something else moved from one place to another. And finally, on these sort of design requirements, just a point that stateful things scale vertically and stateless things scale horizontally. It's really easy to scale a stateless API server across a bunch of nodes by just spinning up a ton of instances of it and having a load balancer that, whatever, round robins between them. Whereas if you've got a Postgres server that you're storing your financial transactions in, you really, really want there to be one instance of that thing. And you really, really want all of the user requests that go there to go to that specific one source of the truth. Just to caveat this, though, what I mean by stateful things, this doesn't mean, so if you're thinking ahead, you might infer that this means that your data services can only get as big as one box, but that's not true, because my definition of stateful things can include, for example, a shard of a NoSQL database. So it could be that a stateful thing is just a container that is part of some larger system, which at the application level is providing whatever big data services. So I'm going to talk through sort of a little bit of the proposed architecture for this. And so what we're looking at here is a container sandwich. It's actually two container sandwiches, one per server. And so the general idea is that if you have containers in the middle here, actually I'll point to this one because it's a bit easier. If you have containers in the middle between a proxy layer and a storage layer, then this is how you can abstract those containers away from the underlying infrastructure. If you have a storage layer that gives you lightweight portable volumes for your lightweight portable containers, then what that means is, and if you have a proxy layer that's controlling the incoming requests, then that means that you can then move those containers around by carefully controlling the storage and the requests that are going to that container at the same time. And so we can pull this trick of live migration, which I'll talk about in a minute. But also in this diagram, we've got this management layer, which I almost glossed over there. And that's where you have to have some of the really complicated distributed systems stuff. So much like in the previous talk about etcd, the management layer, it's really important that whatever you put in here has strongly consistent group messaging semantics. And that means that it needs to cope with all of the sort of various hairy edge cases of network partitions and so on. And so we need to use something like Raft or Paxos, which has been proven by people who are much smarter than me to actually be correct in under all possible distributed systems behaviors. And on top of those, on top of tools like Paxos or Raft or Zookeeper or etcd to refer to the implementations, you can then build these distributed consensus protocols, which can allow the machines basically to chat to each other and say, hey, I'm still here, or hey, I'm getting busy, can I give you some of my work, and that sort of thing. And what's also important here is that all of these things have no single master, so any one machine can fail, and the management layer itself can be resilient. So I'll talk a little bit about the storage layer that was sort of the bottom right on the diagram. I'm a big fan of ZFS, although the authors of ZFS pronounce it ZFS, so I'm going to capitulate and call it ZFS. Because I think that ZFS is a really beautiful storage analog to containers for compute. And I mentioned this earlier, actually. I said, so what you want is lightweight portable volumes for your lightweight portable containers. And the really nice thing about ZFS is that you can allocate thousands of very lightweight file systems to match each of the containers that you have on one host. And those file systems can then be independently snapshotted. And there's a tool called ZFS send and receive, which means that you can move those snapshots around in an extremely efficient manner. And so this is a really key building block for building this sort of storage system that we need to be able to run stateful containers in clusters. And so along with being able to independently snapshot and replicate these volumes, the sort of idea that I'm trying to get across here is that you could have a cluster of a bunch of machines, maybe say 10 machines. Each machine could be in a master role for 100 containers with 100 associated file systems. And the system would automatically allocate some number of slaves according to what I call the redundancy invariant. So basically what this means is how many copies do you want of each bit of data? And so you could allow the system to automatically say, well, let's just pick the machine with the most free disk space and set up a replica for each of the file systems over there. And it would be nice if such a system would automatically allocate slaves in that fashion and start replicating the data automatically. So the next bit is containers, and this is the shortest slide on the talk. Docker, obviously, because Docker is taking over the world. In a previous project, we used FreeBSD jails, and prior to that, Solaris zones were often used in the enterprise. So this container stuff isn't new, but I'm really, really happy that it's taking off finally. And so we're using Linux. And then on the networking side, so in order to be able to actually do this moving around of stateful things, it's important to be able to carefully manage where those network connections are going. And in a previous incarnation of what I'm about to show you, we built this thing called Awesome Proxy. And Awesome Proxy would allow you, basically, the idea is with distributed systems, we're trying to turn a group of computers into something that looks and behaves like a single computer. So it'd be really nice if we could just send any request to any machine and have it like internally reverse proxy to the right backend for whatever that service is. So we went down this road of, like, in Awesome Proxy, building support for a bunch of different layer 7 protocols. So we built an HTTP proxy, HTTPS, POP, IMAP, SMTP, FTP, MySQL, SSH. That was fun. And so we ended up building this sort of what looked like a flat architecture where you could send any request for any of these protocols to any node. And what was nice about that was that if an application server wanted to talk to its database, it just talked to localhost. And it got tricked into thinking it was talking to the database on localhost, but it was actually talking to the proxy that could be talking to the database via the proxy. And that database could actually be in flight. It could be being moved from one machine to another, and the client didn't notice. So that was a really neat trick. However, in the Docker ecosystem, we discovered that people were smarter than I was when I built Awesome Proxy and realized that you can actually divide the world up into routes and links. I'm a big fan of Docker links. So the idea with routes is that that's sort of the external interface to your cluster. You can, and basically for external interfaces, we probably only need to support HTTP, HTTPS, and TCP. And then you can implement whatever else you like within that. But links are connections between pairs of containers. And that's how your application server can talk to your database server, for example. And so the nice thing about that is that you only need to support TCP, because when you know where a connection is coming from, you can route it to the correct place based on having declared the relationship between the application container and the database container ahead of time, for example. So that's sort of where networking is panning out, and I think that's a really powerful model. And then so I talked about live migration being sort of the crux of improving the operational manageability of stateful containers in production systems. So I'll talk through how that live migration process works. And so what we've got here is a picture from the documentation for Flocker, by the way, which I'll talk about in a minute, which is our open source project that does some of the things that I just talked about, but not all of them. And so what we've got here is user requests come in the top, they hit the proxy layer, and the requests could end up going to, for example, a MongoDB container here, and that MongoDB container has an associated volume with it that's backed on this sort of backing store here. And you can actually move this container from this physical machine to that other physical machine by going through the following process. You can pause incoming requests at the proxy layer. Flocker doesn't do this yet, by the way, but it probably will in the future because the previous thing we built did. So it can pause requests at the proxy layer. It can now allow any in-flight requests to complete through to that. And at that point, there are no requests. We've drained all of the requests and new ones are waiting. We can then shut down that container and take a final snapshot of the volume. And then because the volume, the diagram doesn't really show this clearly, but because the volume could have been being automatically replicated to this slave over here on this other node, we can copy what is typically just a few hundred kilobytes of changes over the network, irrespective of how big that volume is. So we can live migrate very big things by having them almost up to date somewhere else. And then we can start the container, we can boot it up, and then we can unleash any requests that were paused here at the proxy layer, and we can do all of this in less than a second in many cases. So this really actually does allow you to abstract applications and containers away from the underlying infrastructure without using any of the virtual machinery. So I mentioned Flocker. What is Flocker? Well, it's the open source project on GitHub that we've released that does some of these things. It has a few pieces. It has an application manifest, which defines a little bit like Fig, and we're actually going to be switching to just supporting the Fig syntax because we're not precious about our YAML. But there's an application manifest which just describes which containers you have and the links between them. And then there's a deployment manifest which describes the placement of those containers. So at the moment, what Flocker is just a way of manually describing where you want to put things in a multi-host fashion. It's going to become more than that in the future, and I'll show you a sneak peek of that just now. But there's then also this network proxy layer, which doesn't do the pausing yet. It just uses an IP tables trick at the moment to reroute the requests. And there's also this ZFS-based storage layer and a command line interface that you can run on your laptop. So I'm going to show you that. And I'm going to hold the mic at the same time. So here we can see a couple of machines. Machine top left, node 1, and node 2 here. And here we've got an application manifest that's a MongoDB instance that references a Docker image. and a volume that's associated with that. And we've got 2 deployment manifests. The first one just shows the MongoDB instance running on node 1. And the second one says, please host the MongoDB instance on node 2. And so using Flocker deploy with these 2 different manifests, we can instruct Flocker to move things around between hosts, which is nice. So now I'm going to copy some examples from our documentation, because I can never remember how to spell MongoDB stuff. And we can see that we've got some data in our MongoDB instance here. And I'm going to insert some data into the database. And I'm sorry I didn't re-record this video for Cologne. I'm saying hello Docker London. And we've also got some beer in our database from a previous demo. But anyway, so we managed to write a row into MongoDB, and it's there. And then we can run Flocker deploy. And at the moment, remember, the MongoDB database is running on node 2. And so what Flocker deploy is doing is it's shutting down the MongoDB instance, it's copying the data over, it's starting it up again, and it's rerouting the network connections. And by the way, using the Mongo client, we connected to, I think, node 2. It doesn't really matter. The point is that the client can connect to either node. And now we can see that the Docker container with its associated volume is now running on the other VM. And if we run the Mongo client, yeah, it was node 2, then we can check and we can see that our data is indeed still in the database. So that's moving stateful containers around from one node to another, which is kind of useful. And we'd really like to integrate things like that into the type of container orchestration systems that people are using today to add support for stateful applications as well as stateless ones. And we released Flocker 0.2 last week. Just a couple of points on the features there. The first feature, the main feature, is two-phase push. So in the previous version 0.1, we did the stupid thing, which was that we shut down the container, and then we copy all the data. And then we start the container up on the other side, and then we reroute the proxy layer. So the amount of downtime for that migration is proportional to the amount of data in your database, which is kind of crap. So two-phase push is a bit smarter. Using this nice feature of ZFS, we keep the database running. We take one snapshot, we replicate all that data. It takes like hours maybe because there's a terabyte of it. And then we shut down the container, take another snapshot, copy just the changes since the first one over the network and start it up again on the other side. So that's pretty useful. We also added first-class support for Docker links across multiple hosts, which I think is kind of cool. And off the back of that, we've got a demo of Elasticsearch, Logstash, and Kibana running on Flocker. And we also added support for environment variables. So yeah, check it out. You can try the demo. We have Vagrant images, so you can spin it up on your laptop. And yeah, feel free to try it out. I'm now going to give you sort of a sneak peek of where we're going with this stuff. And yeah, so there's a big fat disclaimer on this demo. This code is not available on GitHub, and it never will be because we're throwing it away. It's a massive hack that I built in 10 days on top of our old code base. But I thought it would be useful to show you sort of where we might be headed with this stuff. And what it might eventually become possible with Flocker. And so the key idea with this demo is that you can treat a cluster of machines like a single computer, right? We already talked about that being one of the principles we're trying to achieve here. What if you could treat a cluster of machines like a single Docker host? So what we did, well, what I did was I implemented enough of the Docker API to be able to run fig up against a cluster. And then the cluster can actually choose to run those containers wherever it likes and also move those containers around automatically if it wants to. And what our previous code base also did was instead of just copying the ZFS diffs around when the user asked it to, it would be continuously taking snapshots and replicating those changes. So you had sort of this live continuous streaming backup of your databases or your whatever your stateful application is, so that it can automatically recover if something fails. And the other thing to note here is that with Flocker, you had to manually specify that deployment config. So what the ops person, presumably in this scenario, so the idea is that the developer would write the application manifest, and then the ops person would probably write the deployment manifest. And they might be the same person. Great, we're doing DevOps, but you've got different hats. Anyway, however, with this cluster, the idea is that you don't have to write the deployment manifest because that's automatic. You can just deploy to the cluster as if it's one big Docker host, and it will just sort everything out for you, including volumes. So without further ado, so what we've got here is we've got 2 nodes in a cluster, and this is just a display of those nodes, and you can see that those nodes are currently running 0 containers each. So it's not a very interesting cluster at the moment. But what we do have over here, which is kind of interesting, is a Fig manifest. And that Fig manifest just describes a Redis application and a Flask application. And you can see the Flask app. It's a pretty stupid little Flask app that connects to Redis, increments an integer, and returns that integer. We can also, the interesting thing here is that the Docker API is not actually Docker. It's the thing that I built quickly. And you can use that to deploy those containers onto this cluster. And you can now see that node 1 is running 2 containers. And indeed, node 1 is actually running 2 Docker containers. And the application works. Hey, presto. You can hit reload, and it increments the integer, and that's all great. We can also use this tool called HCL Move from our previous iteration of our product. And what I just did there was run HCL Move, and what really quickly happened there in less than a second was that that stateful container got seamlessly moved from one node to another, and you could see that everything carried on working. And now what I'm going to do is I'm going to shoot node 2 in the head. So that's it shutting down. And this is normally when you get paged. About 60 seconds from now is when you normally get paged, right? Because Pingdom is monitoring your system, and it's like, it's down, can't ping it. That's not very good. And so what's happening in the background here is that the other node in the cluster was listening to heartbeats from node 1, and sorry, node 2, and node 2 is now no longer sending any heartbeats. So node 1 is like, okay, I'm going to have to do something about this. And what it does is it decides to try and recover those containers using the latest copy of the data that had been continuously replicated to it. And so we can see a countdown over here. So in 5, 4, 3, 2, 1, node 1 is going to recover all of the containers with their data that was running on the other node. And you can see that the application is now back up and running within 45 seconds, and you managed to get a good night's sleep. So that's sort of where we're going. We're nowhere near this yet. And as I said, what we absolutely don't want to do is just build this thing as a single monolithic thing, which you have to use it and nothing else. We'd much rather that you were able to use this with tools that you want to use, like CoreOS. And so we're really interested in looking at an integration there. And what we really want to do is provide the stateful piece of this puzzle. And I think that could be a genuinely useful addition to the Docker ecosystem. So thank you very much. Any questions? Check out the GitHub and come and hang out with us on #ClusterHQ on Freenode, please. We love people on IRC. And by the way, we are hiring, and we are hiring in Europe. So cool. Thanks. So questions? Anyone?
Which one gets the CoreOS?
ClusterHQ t-shirt.
So when you move containers together with a state, obviously it is possible that some larger transaction or something like that is going on.
Yes.
Surely you have to somehow interrupt that. Because if some of the state is not persisted to disk, but it's actually running in RAM, then it will be lost.
Indeed.
But
so
I guess there's no good answer to that problem, is there?
Well, so there's a trade-off. And so so you were talking about a long-running transaction that needs to be interrupted when you move something around. Basically, so you saw that what we were trying to do was to drain the network connections, pause new incoming connections, allow in-flight ones to complete, and then do the move once there was nothing going on at the container layer. If there's a long-running transaction or some connection that isn't going away within a certain threshold of time, then you have two choices. You can either kill that connection and the application just has to deal with it, and then you can move the container, or you can give up on the migration. And so in the previous version of what we built, there were actually two modes for a live migration. There was forced and non-forced. And so what you could do is, if the reason that you're moving something around is that you think a machine or the system itself thinks it's getting a little bit busy and it would be kind of nice to move that container somewhere else, then it doesn't matter if the live migration doesn't work, we can go and try it on another container. But if that machine is definitely going down in 10 minutes because someone's going to the data center to pull the power cables out, then you probably are okay with losing one or two transactions or user requests, whatever, and you'll just take the hit. So that's the trade-off that we made. Yep.
And they love to drive exports from different stuff. There's plenty of data that goes up and down in the database, and then the index is built on it. And even with a cluster, we have sometimes that scenario where a whole cluster is down. And I wish to have such stuff like Docker or storage direct in there. So we can problem when, for example, the index is built with the data, and if it goes down, data you can bring it up to lose some part of the data and to release them.
Sure. So that's actually the desire to avoid rebuilding an index on the data node or data container is actually a good argument for being able to recover shards of an Elasticsearch cluster independently of the Elasticsearch replication protocol. And so, yeah, you will be able to do that with Flocker once we support replication in Flocker, which we don't yet, but we will soon. Cool, thanks.
If you have a data volume with a lot of large files in it, and you only make very small changes, are you able to detect these small changes and only replicate these changes to the other files?
Yes. So we're sort of riding on the shoulders of giants here, because by using ZFS snapshotting, sorry, the question for anyone who's watching, it was if you have large files and you make small changes within those files, can you just replicate the changes within the file? And the answer is yes, because ZFS snapshots and send and receive only, they only transmit the blocks that have changed on disk from one snapshot to the next. So it's very efficient.
If you have a PostgreSQL service running,
Mm-hmm.
and maybe you have the data on the. If you have PostgreSQL running and maybe you have the data on ZFS volume, would you still use the ZFS replication, or would you rather rely on the replication that PostgreSQL does?
Sure. So it depends, and you can do either. But I think that there's something to be said for having this sort of distinction between operations people that have the job of managing a cluster of containers, and that's the only thing you know about the workloads, is that they are containers and they can run any software. And to be able to, I think there's a lot of value in being able to manage those containers independently of whatever's running inside them, in the same way that you can with VMware vMotion, for example. Well, that said, it may well be the case that you want to have Postgres replication configured as well, and it could be the developer's responsibility to do that. And so you could say that you do or you don't the system to take care of some replication for you. There's definitely trade-offs, and yeah, I think that there's room for both.
Just a simple question. Does it work with CoreOS?
Not yet, but we're working on it.
Okay, thank you.
The main barrier at the moment to getting it working with CoreOS is getting ZFS running on CoreOS, which we've done. We have ZFS working on CoreOS. It would be great to collaborate with CoreOS, because we're happy to provide resources to maintain that kernel module and ship updates to it whenever CoreOS ships updates. And then there's one other issue, which is that the way that people package and software that runs on CoreOS is in containers. And so can you distribute something that can talk to ZFS and create file systems outside the container from inside the container to be bind mounted into new containers that get created on that system? Not yet, but I think we've got someone working on that. It seems like it's feasible. We just need to like work around the mount namespace in Linux, but it's definitely possible. And I mean, we'll do it faster the more demand we get for it. So if people are interested in it, then please show up in IRC or shout out now and let me know that you want that thing. Okay, cool. Great, I can take that to the product meeting on Tuesday. Thank you. Yeah, so the question was, do you see advantages to using a real clustered file system rather than doing what we do here, which is basically local storage with replication? Yes and no. We looked closely at ClusterFS and Ceph. Clearly, Ceph actually provides block storage rather than POSIX file systems. And I feel like with containers, there's sort of an impedance mismatch between block storage and what containers want. And it's difficult to get the sort of density you want if you want to give each container its own block device. I heard a story actually of someone trying to attach 1,000 EBS volumes to one big EC2 VM, and it just all falls apart because each EBS volume counts towards the network traffic. And anyway, so you can have a bad time doing that. But I mean, the question in general is like, why not build this on top of a real distributed file system? I think that the semantics that you get from a real distributed file system are more than you need to solve this problem. To the extent that you actually are being kind of wasteful by using a real distributed file system. And what I mean by that is a real distributed file system gives you a global namespace, meaning that any node can talk to any part of the distributed file system from anywhere. But what you actually want, what you want for container storage is much, much smaller than that. It's a narrower constraint because you want one node to be able to talk, read, write to one volume at a time. And so to me, it seems sort of more elegant to have this sort of thinly sliced local ZFS that's replicated to sort of sharded to a number of nodes. And you also get better performance out of using local storage, and you get nice features like L2R Conzil, which can really help with performance. And I mean, as an example of that, there's issues with ClusterFS with small file performance. And a lot of these workloads do things with small files. So I hope that answers the question. Anyone else?
Have you some experience with performance like 10 gig Ethernet or InfiniBand or so, when you have lots more of data, so when you write very aggressive in your storage, then you must replicate it. Have you some experience on load test or whatever?
Yeah, so we did a bunch of load testing with the previous platform, which, as I mentioned, was FreeBSD jails and ZFS. But I think the architecture isn't changing much. The same sort of basic performance metrics should apply to the new system we're building. And we found that we could get up to 10,000 containers per machine. And when we were running it in production, we would often see that the amount of the bandwidth used by the systems on doing replication was much lower than the bandwidth used by the systems just serving request traffic. So that was, I mean, it's not super rigorous, but that was a nice data point to indicate that at least with the sort of workloads where the data doesn't churn that much, and where you've got lots of like inbound requests, then it's entirely feasible to run this on gigabit or 10 gig Ethernet. Yeah. Of course, when you do synchronous replication, then it's a different question, and you want to look at sort of minimum 10 gig, and that's also something we're working on at the moment. Anyone else? Cool. Okay. Well, thanks very much. Okay.
Thank you. And for the last talk, Shane and Moritz, Mirko. Shane will do the presentation. Okay. So, welcome Shane from the Open Innovation Network.
So, hello everyone. As you can see, I'm wearing a suit, and that's obviously an ominous sign. Lawyers cannot be far behind. I'm with Open Invention Network, OIN it's called, and we're a community organization that exists in the background to help support cool technologies like we've seen tonight. OIN has a community of patent non-aggression. See, I told you lawyers were coming. What we try and do is make sure that Linux system technology, which now covers 2,200 software packages that we call the Linux system, is covered by a non-aggression pledge by our members. Everyone agrees that they're not going to use their patents against this technology and automatically grants everyone else in our community a free license to the Linux system technologies with respect to their patents. This reduces risk, and it means that we avoid having conflict around the Linux ecosystem. What's really cool is that we are engaging with lots of small companies as well as huge multinationals. We were founded by multinationals. We were founded by companies like Red Hat, IBM, NEC, Sony, Novell. Google came on board as the seventh founding member. We've got European companies like Philips as founders. But we are a community of epic proportions. We now have 1,120 participants. We just announced 1,100, but we've accelerated. We're at 1,120 participants in this community, and we've got a lot of really cool startups. We've got really scaling startups like Docker. We've got slightly older startups like Dropbox. I mean, old. And we have, of course, other startups like Google, which have matured a bit. We also have tiny companies. We've got companies in Europe with just 2 or 3 people. We've got some one-person companies. Everyone is welcome. Our community is unique. What we do is we want to prevent anyone having patent aggression on the Linux system. Everyone makes the exact same promise and gets the exact same benefit. It doesn't matter if you're Fujitsu, they're in our community, or you're a one-person startup. You pledge that if you have patents, you're not going to use them against the Linux system. And you get the same promise back from everyone else in our community. And that's it. There's nothing else. There's no trick. It's all about this patent non-aggression. What I'm here tonight for is to let you know about us, because many people don't notice OIN. We are a background thing. Our job is to reduce risk and to support people. But we don't have a marketing department. We don't have products and services that we sell. We don't make money. All we do is collect non-aggression pledges. And perhaps sometimes in Europe, we haven't got the word out far enough. That being said, out of our 1,120 participants, over 50% are from the European area. That's because of all the SMEs here. We've got a ton. But there's a lot more of you. And you're welcome. And it's the right time to join in. Not to have any scaremongering or anything, but sometimes in Europe, there's a perception that software patents are not an issue in Europe. That's not quite true. The EPO is granting software implemented inventions all the time. We have observed software tension in Europe from non-practicing entities, trolls. That's been a recent development, but it's growing in Europe. It's happening with speculation. OIN is not a magic bullet, but if you're involved in open source technologies, if you touch on Linux, if you're doing stuff around, say, Docker, come and look at us. We're here. All we want is a non-aggression pledge, and we're able to give you a ton of pledges in return. And the whole idea is that it's going to make anything on the legal sphere regarding patent a lot easier for you. It's going to reduce your risk, and you can focus on your product, your startup, whatever. Anyway, Mirko and I are here today. I'm based in Japan, Global Director of Licensing, but based in Japan. Mirko's on our community side, Linux Defenders it's called. He's based here in Germany. What we'd love to do is to give you our cards, let you contact us and ask us questions, and who knows, maybe you can join our community too. It would be awesome to welcome you, and we're going to be here to circulate and answer questions right now as well. Okay, because I don't have any cool technology, I'm going to end it there, but thank you. Wow, what can you do? Oh, you got something?
I think Shane forgot one of the most important things of our community, and that is all it takes for you to join is a non-aggression pledge. We're not like insurance peddlers. Like, you don't have to pay anything. Membership is free. Sounds a bit weird, maybe, but you have to really look at the concept. We are building a non-aggression community, and that means even the smallest startup is welcome, and there is no membership fee. Your cost is a non-aggression pledge. And if you look at the technologies that we're covering in our Linux system, which is the scope of our non-aggression agreement, it's the stuff you work with every day. So you don't want to get sued by some patent troll holding a patent on file systems that replicate. And if you want to be safe from that kind of threat, because they're really that generic, then look at the license agreement that says, I promise non-aggression in return for a non-aggression pledge from the other 1,100 companies in the pool. And as Shane said, there are small one-person companies in there, and there are large multinational companies in there that hold thousands of patents. So you're really on a safe side. And all it takes is reading the license agreement, agreeing to the goals, and then signing up. Thanks. I'll be here for questions if you have any.
All right, thanks everyone.
Thanks, everybody. Since the room is still full, I hope that you're all leaving like and getting tired, and because I have some t-shirts, but there are not enough t-shirts, and I don't know how to figure out to give them away. Yeah. Actually, yeah, that's perfect because they're American XL, extra large. So yeah, maybe the bigger ones have better chances to get a t-shirt. So they're just lying here. Grab one if you like to get one. Okay, thanks for being here, and drink some beer, and yeah.
So thank you very much for watching. This video, the stream, will be available for quite a couple of days. But then we will cut the video into tiny pieces and republish it on the Giant Swarm YouTube channel. So please check out the Giant Swarm YouTube channel in a couple of days, and you can listen and watch the speeches of today's people again. So thanks again for watching. The stream was powered by NERDHUB, so check out nerdhub.de and come back later on. See you guys. Thank you for watching, and goodbye.